VR games, such as Emergence or Humanity, focus on user experience in crowded environments. Equally, VR serious games, such as Evacuation Training, have gained a lot of interest in recent years. In these experiences, producing plausible trajectories can be a significant computational cost for real-time graphics engines, especially for standalone VR devices. We explore how real users perceived computationally inexpensive rectilinear trajectories in an immersive environment. To do this, we simulated a large crowd and compared the perceived realism of synthetic trajectories and trajectories extracted from real data. We then measured the impact that the plausibility of the trajectories had on the perceived immersion of users. The real trajectories came from a commercial video of a crowded pedestrian crossing, containing 280 pedestrians over 30 seconds. Trajectories were extracted by tracking pedestrians' heads with an open-source computer vision software library. By measuring different features in the video, we estimated the size of the scene as 20 meters by 40 meters. We adapted the rectilinear algorithm proposed by Barut in order to simulate the pedestrian crossing, generating the trajectories of each of the simulated agents. Each of the pipes represents the trajectory of one pedestrian, while the radius represents the clearance between pedestrians. The vertical axis represents time. We took our inspiration from locomotion synthesis work performed by Holden in 2017, based on deep learning. Phase-functioned neural networks were used for character control. We recorded the joint positions to avoid performing the simulation in real time. This was required for performing the experiments on untethered devices such as the Oculus Quest. We ran an initial experiment to understand if the adapted rectilinear algorithm produced trajectories that were as realistic as those extracted from the pedestrian crossing video. We generated two synthetic simulations that were rendered from two different camera angles. Before viewing each video, the participants were instructed to pay particular attention to the trajectories and speeds of the pedestrians. After viewing each of the videos, the participants were required to complete the perceived realism questionnaire. 153 participants performed this experiment remotely. There were 4 possible response options: realistic, plausible, unrealistic, and impossible. 75% reported perceiving the rectilinear algorithm trajectories as either realistic or plausible. These results validated the plausibility of the rectilinear trajectories in counterflow conditions. More details are provided in the paper. The second experiment was performed in virtual reality and measured how users perceived the realism of the rectilinear trajectories compared with the real trajectories. We also aimed to understand how much trajectory realism impacted the level of immersion experienced by the participants. We developed an application within Unity targeting Oculus Quest 1 or 2. After the experiment started, the participants were instructed to focus on the trajectories rather than the avatar animations or the environment details. Afterwards, participants were asked to rate the observed trajectory's realism via the same scale as the first experiment. We recruited 40 participants to take part in the experiment. The perceived realism was again recorded via a questionnaire with 4 levels: realistic, plausible, unrealistic, impossible. Results showed no statistical difference between the perceived realism of linear trajectories and real trajectories. Also, the results showed no statistical difference for the immersion level experienced by participants between real and rectilinear trajectories. These experiment outcomes highlight how spending computational power for trajectory realism does not necessarily increase the levels of perceived realism and experienced immersion in a high-density crowded crosswalk setting.